Hello. Since we didn't get to go over some students' homework questions on exercise 12F, I thought I would just explain the work that is here in the Unit 6 answer keys document. Let me make this bigger. There we go. Now, exercise 12F, I did one in class, and I did the phase portrait in the screencast after class, but let me just go over a couple of these again. You already know how to solve. But now this phase portrait is interesting because we have one positive and one negative eigenvalue. In order to do the phase portrait, you just need to know the eigenvalues and the eigenvectors. Remember, the first thing we do is draw the eigenvectors. All right, and you should note which eigenvalue they're associated with because that's going to determine the direction of all the other lines. And so here, this is the eigenvalue +4. So this vector is associated with eigenvalue +4, and this vector is associated with eigenvalue -3. This is why these arrows on this eigenvalue are pointing towards the origin. Negative eigenvalues will have points along their vector line going towards the origin. Vectors associated with positive eigenvalues will have points going away from the origin on their vector line. Now, in order to draw the phase portrait, meaning the general direction of all the points, for a positive and a combination of one positive and one negative eigenvalue, well, to find out what direction all the points in each of these 1, 2, 3, 4 spaces are going in, we just follow the arrows. So in this space, all the points are going to start in this direction and they're going to curve around and then follow in the other direction. Same here, starting in this direction and then curving around and following. So you can see that we're just following the arrows. All right, starting there, going here, and then here. We're going to start here and go this way. Now for the next problem, so problem 1A2, I just found the solutions, or rather the approximate, solutions to this coupled differential equation. All right, so this is our solution. I found the A and B values, but we don't need these A and B values. You don't even really need the solution in order to draw the phase portrait. What we need simply is the eigenvalues. So here, notice we have two positive eigenvalues and their associated eigenvectors. All right, so the eigenvector associated with lambda 1 was 1, 0, and so that's this guy. And since that was a positive eigenvalue, the points will go away from the origin. So that's why I put these two arrows like that. The eigenvector associated with lambda 2 was 1, 1, so that's this vector right here. Again, since this eigenvalue is positive, the points are going to go away from the origin. Now, I'm going to switch screens real quick, just as a reminder, oopsies, of what we said about the different types of combinations of eigenvalues. Here we have two real positive eigenvalues. So this was explained in the screencast on Monday. When we've got two real positive eigenvalues, all points will move away from the origin, starting along the vector of the lesser eigenvalue, going towards the vector of the larger eigenvalue. And this makes a little bit of a curve. Like, we don't know exactly where they turn, but we know the general directions. So if we look at this one again, two positive eigenvalues, 1 and 3, well, we're going to start along from the origin. We're going out from the origin. Remember, all these arrows are pointing away from the origin. We're going to start along our lesser eigenvalue, and then it just sort of curves up and follows the same pattern to be parallel to the vector of the greater eigenvalue. So that's in that area. Same here. We're going to start along the vector of the smaller eigenvalue, and it's going to turn around and start to follow the vector of the greater eigenvalue. Same in this direction. It starts along here, and then it curves and starts going parallel to that vector, and same here. And so that's why we see these little swoopty-swoops in your answer key or in this key. And now I just did one last one where we had, I believe this is two negative eigenvalues. Yes, all right. So this one we found our two eigenvalues were -3 and -4. These are the associated vectors. So again, I drew these vectors, and again, the direction of the points. Now, since these are both negative, all points are going to go towards the origin. All right, so the vectors, the points along an eigenvector for a negative eigenvalue are going to go towards the origin. And it's going to follow a similar pattern as the other one. It's going to start along the lesser eigenvalue, meaning the greater negative one, right? And go towards the greater eigenvalue. So that's why we see these points here. They're starting along the eigenvalue, the vector associated with the eigenvalue of -4, and then they turn and they start going parallel, as parallel as possible to the eigenvalue of greater value. Same, these and these. And then I didn't do these little spaces in here because it was just too tiny, but these will also do the same thing, all right? So they're going to start parallel to this eigenvalue of lesser value, and then they turn and they start following this vector of greater value. And that's how we can see they're following that same direction. So that's just an explanation of how these phase portraits were drawn. You can take a look at the work here. If you have any questions on the algebraic work that we did, please send me an email. And if you have any further questions on the phase portraits, review the screencast from Monday and then send me an email. Okay, bye.